Hello everyone, welcome back to my YouTube channel. So today in this video, I've decided to pick a topic of machine learning and artificial intelligence, which is evaluating machine learning models fitting on data sets. This is a topic which I believe becomes very handy, especially when you are gauging or testing the performance of your machine learning model and also identifying what actually went wrong with your machine learning model, experiment tracking. So it's linked with envelopes as well. So when you actually see model selection, model evaluation is something that any machine learning practitioner, professional, or even researcher has to be aware of. So, by the way, for your information, I also have posted few polls on the community section of my YouTube channel to actually, to understand that what content are you actually looking for in my YouTube channel. So with the polls, I came to observe that data structures and algorithms is the most voted one, and the next comes data science topics, and finally also the web development and full stack engineering. So I would be making more upcoming videos, so stay tuned on my YouTube channel for more content on CSE. So today I decided to take a machine learning concept. This concept, even if you're a beginner or even a advanced professional, then I would say that this topic is a crucial one. So let me introduce firstly to this topic. So when I talk about evaluating machine learning models, you are actually you're evaluating it on the test data set. So a machine learning model, you're training it firstly on a data set, right? And your data set should be firstly split into some part of the data set should be given for training and some part should be for the testing. If you've heard of a very common term, which is train test split. So when you talk about evaluating machine learning models, you're evaluating it not only on the train, also on the test data set. There are three scenarios which are commonly occurring in any machine learning models when you are actually, the results you get. So what are those, and what are the preventive measures for actually overcoming if there is any problem as such, in order to achieve an ideal case, an ideal scenario. So, in the field of machine learning, achieving the perfect balance or the equilibrium between model complexity and generalization is a fundamental challenge. It's of course it's very difficult in practical scenarios when you're dealing with data which is too noisy, or a data which is very less in quantity, or we can say that when you have dearth of data, you don't have actual relevant data for your problem, because data collection is again a task before, prior to training your machine learning model, or even after you have collected data, the task of performing cleaning in the data, then data engineering, setting up the system infrastructure for data, to organization of the data, and also feature engineering to actually identify or select which features are actually will be able to determine the prediction of your model, or be prediction or classification for your task at hand. It is a challenge. So when you talk about those terms, in order to achieve, your model should not be too complex. If you are talking about in terms of complexity of your model, if you're going with directly deep learning model, which is having, or a neural network which has lots and lots of neurons and features, connections in it, but they do not actually, they're redundant, or those features are not actually serving any of any feature importance, right? If you talk in terms of feature importance, they're not much significant. So when there is a lot of complexity in the data, the model is not able to generalize well on the test data set or the unseen data set. So when I talk about in terms of generalization, it means even though you have trained your model on your training data set, on the test data set or the validation data set, which is other than the training data set, your model does not perform better. Now, if you talk in terms of the ratio, the common question to be addressed over here, if you're a beginner, that what if you are talking in terms of train test split, how much percentage should be given to training and how much for testing? So it totally depends. I would say a good ratio would be 70% for training, 30 for testing. Again, it sounds a bit theoretical, so I would say it again depends on your the problem statement at hand, or of course the data, the what quality of data, and the number of features. So the ratio can even be 20, again 80 and 20. The highest, the higher one, the higher proportion should be given to the trained data set, and the less one to the test data set, to actually test the performance of your model. Now, overfitting, the three problems which I was talking about, or the three scenarios which occur in any machine learning model. The first two are problems. The last scenario, or the last case of your model would be the ideal case. So the first two are overfitting and underfitting. The next one, the last one, would be the ideal case, which is something called as bias variance trade-off, which we should all aim to accomplish in any machine learning model project. So when I talk about overfitting and underfitting, they're very common. and they hinder the performance of predictive models. So what do you think will hinder the performance? So now see, this performance is again subjective. It can be, you can actually measure the performance of any machine learning model through various metrics. Now the metrics can either be accuracy, you can even go with precision, recall, or F1 score, AUC, ROC, they're different metrics. But if you're, very new to what these actually mean and you just know accuracy, I would say that it's not just accuracy you should focus on. There are other metrics of evaluation as well, and it depends on the data, the features, and various other factors. But in the context of this video, let me give you an idea as to how to achieve an ideal case in any after you've evaluated your machine learning model and you've seen that there is overfitting and underfitting occurring. How do you actually achieve an ideal case? So in order to achieve this bias variance trade-off, since I thought bias and variance, these are again two terms. So bias is like something like assumptions, if you've heard in that in terms of mathematics and probability. So bias means assumptions. So some incorrect assumptions. So that is bias. And when you have high bias, that is where underfitting problem will occur. And in underfitting, you have less variance. Whereas in when the variance is too high, and variance is nothing but, as the name says, it's high. Your model is very sensitive to fluctuations in the data, or you can say a model when there is a change in the data and the data which is unseen, you're asking the model to you give some prediction or result on the unseen data. Your model does not perform well on the unseen data because it is not able to generalize well on that, but because it has been trained very finely on the training data set. So that is where you have high variance in the data. So to achieve a low bias, now see, bias, a very high bias and a high variance is very, you see, it's not good for your machine learning model. So in order to achieve low bias and low variance in your machine learning model, you need to have bias variance trade-off to develop robust and accurate ML models. Coming to this first problem or the first scenario in your ML model to actually evaluate the model fitting on your data set, that is overfitting. So when your model becomes overly specific, now when I talked about your machine learning model being very properly trained on your training data set, that it's actually even capturing noises in the data. Now this is very, again, depending on what kind of data your data, if you have properly cleaned the data set, but there are some even it's bound to happen that your machine learning model is trained well on the training data and does not perform well on the test data. So there are some ways or some techniques which come handy for you in order to avoid overfitting in your machine learning model. So how you could actually do that? So when your model is becoming very specific, or the complexity of your model is too high, so it happens when your model is attuned or very finely trained on the training data, capturing noise or random fluctuations instead of general patterns. You should always aim to achieve generalization in your model. So your model should be able to achieve, rather than just capturing any random fluctuation or in the data or even noise in the data, it should be able to capture only the general patterns in the data, so that or the relevant features in your data. So in the complexity, in such cases, attempting to fit each training example flawlessly is where your model is becoming problematic. That is what's causing problem. So while an overfitted model may exhibit exceptional performance on the training set, so even if it gives you like around 90%, more than 90% on of the training accuracy, but the test accuracy is too low, and there is a huge gap or the huge difference between your training accuracy and the testing accuracy. That is where overfitting is occurring in your machine learning model. So that is where it's failing to generalize well on the unseen data. Key indicators of overfitting include an extremely low training error and high validation or test error. So this is self-explanatory. A low training error and a high test error or a validation error. The graph for this overfitting will be too curvy, by the way. So if you plot and analyze this performance of the machine learning model and no overfitting scenario, you will see a very curvy graph. It's not a straight line, because a straight line indicates a model is performing, generalizing well. And again, it's just not the straight line, but your model should be able to fit on all the data points. So when it's able to a curvy model where it is actually passing through majority of the data points which are training coming in the training data, but on the testing data none of the points are actually I would say aligning with the line of fit. That is where you can say overfitting is happening. So coming to the next scenario, which is underfitting. This is again a problem in machine learning models. This is when the model fails to capture complexity, in contrast to overfitting. Now underfitting and overfitting go opposite to each other. So underfitting is where you get very low training error as well as low testing error. So underfitting, it occurs when model is overly simple, in contrast to overfitting where it was complex. Over here, it is very simple model, failing to capture even underlying patterns in the trained data. Even in the training data or the test data, it's not able to even capture any underlying patterns. it suffers from high bias. So where there's high bias, which is it is tending to overlook important relationships, resulting in suboptimal performance on both training and test data. That is low training and test accuracy. And some signs include high training and validation errors, indicating the model cannot accurately represent the complexity of the problem. So especially when you have a complex problem and your model is failing to actually perform, give you good results for that particular problem, your model is too simple to actually capture even general patterns underlying in the data. That is where underfitting is bound to occur. Now, what is the ideal case? The main purpose I have made this video is for to give you clarity as to, in any machine learning model project, you have to have the ideal case. Of course, it's very difficult in the practically. If you talk, you need to have the domain knowledge, a lot of knowledge about which model to go with, some of the techniques. And also in this video, I would like to introduce you to what is bias variance trade-off. Although you have encountered overfitting, underfitting, and we will sometimes think that if they have achieved 100% accuracy on the training, it's just the training accuracy you have to go with. No, it's not that. Especially for the beginners, it's not just that you if you have 100% in your models perform, it's too well performing on the training data, it does not mean that your model is actually giving good results. It means your model has overfitted, because it's not actually practically, in the practical conditions, if you talk, it's not possible a model to give 100% accuracy. Especially it occurs in the imbalanced data set, when you see that there is overfitting happening a lot, and you cannot just go with accuracy measure, you need to consider the other metrics of evaluation as well. This happens a lot when you're dealing with imbalanced data. There are other factors, other scenarios as well, where such cases are take place commonly. So that is why there are a lot of I would say MLOps tools to monitor all these problems, or even experiment tracking tools, or even automation tools to actually automate this entire workflow, because people who do not have the much domain knowledge as to which machine learning model to go with, what hyperparameters to give. Now this is again a very important topic. Hyperparameter tuning is a technical term in machine learning, where you actually have to identify what are the suitable set of hyperparameters, or the indicate the factors, the parameters you have to give. Be it, it can either be the number of epochs, it can be the number of layers, or even the train size, test size. What is exactly the value you have to provide to any parameter, so that it will give the correct results, the most ideal results. That is hyperparameter. So such scenarios, I would say there are different auto ML tools also which came up, but again it boils down to achieving a ideal case, which is bias variance trade-off, a balance between both bias and variance. So it is the core of model selection and performance optimization. Optimization is again for related to performance, model performance, which is to achieve good results in terms of accuracy, precision, such that your model should be able to give correct predictions, or correct classification. See, if you talk in terms of, again, machine learning can be the supervised machine learning, where you have, if you're new to supervise, and it is just you're training a model on labeled data set. So labeled data set, as in, or you have feature or the target variable already present in the data set. So prediction, classification, they come under supervised learning. On the other hand, unsupervised learning, there is a machine learning algorithm called as clustering technique in unsupervised learning, where you are operating on unlabeled data. So your model should be able to generalize on unseen data, but it is unlabeled data where your model is trained on. So, okay, so your model has to learn by itself. It has to identify the underlying patterns in the data by itself. It is not given any supervision or training. Then comes reinforcement learning, which is again a third type of ML, which is advanced, and there is no human intervention over there. It's just that the model is depending on its environment to actually by trial and error only, it's going to identify which uh, path to actually go with. So it comes more handy in game development. So in reinforcement learning, the model, or there we have something called as agent there, the reinforcement learning agent, which is depending on its environment to correct itself or penalize itself when it makes a mistake, and when it is giving a correct result, it is given an incentive. So that is by trial and error method. So that was just about the three ML types, the machine learning algorithms. So in any case, you have to achieve bias variance trade-off, which is model performance optimization. So bias represents the model's inclination to make simplifying assumptions. That is why we had seen that it is linked with underfitting. Where underfitting, we have seen that it is having high bias because of the fact that the model is very simplistic. leading to systematic errors or incorrect assumptions about the data. Variance, on the other hand, is where in overfitting we have seen overfitting models is overfitting when it has too high variance and low bias. So it refers to the model sensitivity or the prone, the how prone the model is to fluctuations in the training data, causing it to capture noise or random variations, as discussed. So the trade-off arises between reducing bias and increasing variance and vice versa. Okay, so the trade-off is happening because these actually bias and variance are inversely opposite, inversely proportional to each other. They're opposite. So if you just like decrease the bias, then you will see the variance increasing, and vice versa. But how to actually set some balance between the two measures, which is bias and variance? That is where it comes bias variance trade-off. So strike an optimal balance between them is critical to minimize both underfitting and overfitting problems. So when you actually overcome underfitting and overfitting, you will see that the ideal case, which is bias variance trade-off, is achievable. Some of the ways to address overfitting. Now that you came to know the most common problem, which is overfitting, even underfitting, how exactly, what are the preventive methods you can follow in order to address overfitting? Now again, see the data. It again all boils down to the data set, right? Your machine learning model. If the data is you are lacking data, then I would say, to get quality data, firstly you have to you can either augment the data. So one of the ways to do that for avoiding overfitting is data augmentation, although I have not listed it over here. But data augmentation is one way, and especially depends on the data. So the data type, if it is an image data or you have lots and lots of images, you can synthetically generate the data through generative AI means, like generative adversarial neural network is one means to do that. Synthetically adding new data, or even just flipping images, resizing them, manipulating different images, or adding different modifications to them, is actually going to add new data, slightly modified data from the data set you have at hand. So that is data augmentation. To do that, even for textual data, there you can do data augmentation techniques. So the next step, the next one of the other methods for preventing overfitting is regularization. Regularization basically is for when you have your models too complex. That is why overfitting is occurring. So in order to reduce the complexity of the data, you are penalizing that. You're reducing complexity by introducing some term called as a regularization constant or a coefficient, which will actually take care of penalizing the loss function. So when I say that, it is where now loss function is again indicative of the error in the model, the error introduced in the model. So also all such factors. So in regularization also there are two types, L1 and L2 regularization. L1, the name, another name for L1 regularization is lasso regularization. L2 regularization is ridge regularization. So do not worry about these terms. They are just, I just want to introduce you some techniques. So L1, so basically these regularization techniques are, if you compare them, L1 and L2. So L1 is lasso regularization, where you are considering the penalty term which I was talking about, the constant, regularization constant to reduce complexity. That term is not squared, rather it's just the mean absolute value of the error. But that in L2 regularization, the same term is going to be squared. So it's going to be a squared coefficient constant rather than just a mean absolute value. So that is the difference where and it is to introduce penalties to the loss function, discouraging excessive complexity in the model. Coming to the next, which is dropout. This is very simple. Now, if you have a deep learning neural network, model, now you know that any deep learning model, it is built of various neurons. Right, neural networks built of various neurons, and it has each neuron is connected through edges or connections. So when you are randomly dropping or deactivating the neurons or the edges, that is where you're introducing dropout. Even if you're training models, you can see that various machine learning codes have some this parameter called as dropout. This is again a hyperparameter, by the way, because dropout, it has to be initialized to some value. If you specify some value to it, it will understand, the model will understand how many neurons or what quantity of neurons have to be dropped, and so on. So randomly deactivating a portion of the neurons during training, preventing over reliance on specific features or patterns. So because see, features, adding more features, adding more patterns, or even adding more neurons, these all are the different hyperparameters which are increasing complexity in the model. Given the fact that overfitting is occurring because your model is too highly complex, and now that you have to address overfitting, you have to decrease the complexity of the model. To do that, dropout comes a very handy technique to do that. Coming to next, which is early stopping. Monitoring validation error and stopping training when it starts increasing helps prevent the model from overheating. This is again very important. Now, see, if you are training the model, you're going on training it, but you don't see any significant improvement in the model's accuracy. Rather than you see that the model's the validation error or the test error, that overfitting is giving you good training, training accuracy, which is less training error. But on the other hand, you see validation error is too high in overfitting. So when you're monitoring the validation error or the test error in overfitting, you see that you see that it starts increasing rather than decreasing. So that is the point where there is no point in for continuing the training of your model, and you have to stop your training at some particular point of time that is called as epochs. So epochs are the iterative cycles, I would say, for training. So they're related to the number of epochs. So basically, when you stop at some particular epoch, be it a 9 or 10 or even 2, a number of values, see, epoch number should be 2, 10, or so on. If you're stopping a certain point of epoch, so it says that you're doing early stopping over there, because in order to address the problem of overfitting. Coming to next, which is underfitting prevention. Now that you've understood how to address some of the ways to address overfitting, underfitting, the remedies are, now that underfitting is too simple model, right? You have high bias, low variance, too simple model. So when a model is too simple, not performing well on the training, neither the training nor the test data, in order to avoid underfitting, you have to introduce some kind of complexity to your model. Now, how can you increase complexity? You can make your model complex by increasing complexity by adding more layers, or increasing the number of hyperparameters can help capture more intricate relationships in the data. Intricate in the sense complex or detailed relationships in the data. So when simple models are not even able to capture, the not even fitting properly on the data points of the training data, you can introduce some relevant features by adding more, transforming the existing features or adding new features to the data, which are actually will help your model to give correct predictions or correct classifications, right? So feature engineering is that process, adding more relevant features or transforming existing features, which can provide the model with, more additional feature to learn from, more additional information to learn from, because your model is too simple. It is not identifying general patterns. So in order to help your model to do that, you can do feature engineering, which will actually prevent underfitting. Algorithm selection is again very, very important in any machine learning project, and be it even if you're a novice or a professional, this is comes very handy, because you, as I've told you, you cannot just do experimentation, trial and error to check which machine learning model will give you good accuracy. Of course, machine learning is all about trial and error, improving accuracy, optimizing it performance, and iterating the cycle. But when it comes to algorithm selection, having domain expertise is very important, where you actually have an idea as to which machine learning algorithm will go well or will be suited for some kind of data, be or any problem statement. So it depends again on the type of the data, the features present in the data, how many features, the number of features of the data, what is the target outcome or the problem statement at hand, business outcome to solve, and the application. So algorithm selection, so if you're switching to more sophisticated algorithm, so the task at hand, if it's a prediction, then there are certain prediction algorithms you can go with. If you've heard of linear regression, logistic regression, so on. If there are classification, you can go with any classification technique. Now, classification, again, it's not that you have to just go with blindly with the most advanced deep learning model. So if you are going, switching, to some machine learning model or deep learning model, which is too complex for your model to understand, that is where you will see overfitting to happen. So switching to more sophisticated algorithm can handle complex relations. So that is one of the ways to alleviate or to solve this underfitting problem. And on the other hand, when a problem at hand requires deep learning to, you have to use deep learning for solving that in a more optimized way. When I said optimize, less training time and less consumption of the resources. So just not using simple regression techniques will actually help. You have to go with deep learning methods or deep learning algorithms. So it again depends on the what kind of problem, the context is, the domain. So that is algorithm selection, which is again one of the aspects, I would say, which comes a concept which any machine learning practitioner should understand. Then graphs depicting the three scenarios we covered. We covered underfitting, overfitting, and the balance scenario, which is bias variance trade-off, right? The three cases which indicate the fitting of your model on a data set, trained data set. So underfitting is where your model is too simple. So this is just straight line. It is not even passing through all the train data points correctly. So this is underfitting, where you have high training error and a high testing error as well. Overfitting, where your model is too curvy. It is not a straight line. It is having polynomial features. There is a right. You have polynomial features over here because there is no linearity introduced here, right? In the overfitting, there is a model is very highly sensitive. You can see the way it is curvy is because it is too sensitive or prone to fluctuations in the data. The moment you give it some unseen example or something which is it is not even trained on, it will give you a very false result or incorrect prediction, which indicates a high validation error, which is not optimal. So that is one reason it is giving such a curve. To actually find a trade-off or a equilibrium between underfitting and overfitting, I mean, not these two, but to solve both these problems and to find a balance between bias and variance, you have this balanced graph over here. And of course, you need to ensure that your data is balanced. So even if you have are dealing with imbalanced data, there are techniques in order to remove imbalanced in the data to make it balanced or to overcome such scenarios. But that is not in the scope of this video. Those require some other techniques as well. To name a few, you have sampling, which is again undersampling and oversampling. It depends on whether you have a minority or majority classes. So that is why you have a non-uniform distribution in the data set, which is imbalanced data set. So you can go with such techniques for finding removing the imbalanced data and dealing with that. This is a balance graph where you have achieved bias variance trade-off. So that was all about the topic of machine learning and evaluating machine learning fitting on data sets which I have picked. I hope I have given you insights on this topic, which and I it's a really important topic. So do share with all your friends to spread the knowledge. Don't forget to subscribe to my YouTube channel to stay tuned, because for upcoming videos I'll be covering more interesting content. Like, share, and subscribe, and feel free to comment on my video if you have any doubts and give your feedbacks. Thank you very much.